So I've been a RF engineer for a few decades now, and one of the fundamental circuit that as an RF engineer design is an oscillator. We use it to up convert a signal or down convert a signal in addition with a mixer. And we also modulate information onto the oscillator and then up convert it to a frequency, for example. So today I'm gonna go over the fundamental of oscillator design. It's once you understand the fundamental, the circuit design is pretty easy to design and understand. To get started, we start with a classical feedback loop amplifier. So here we have a input Vi, and it goes through a inverting amp. So we have a negative G. That means like it amplifies the signal and also changes the phase from 0 degrees to 180 degrees. That's what an inverting amp is. And then at the output, we feed through a feedback network called beta. And because it's an inverting amp, we have to subtract. Okay, so that's the classical feedback loop amplifier. So to understand the fundamental of oscillator, we have to derive the transfer function of this feedback loop amplifier. So at this particular point here, oops, made a mistake. At this point, it is Vi minus beta times V out, right? So beta goes through V out fed through beta. So at this point is beta times V out. And then at this point at the output, it gets amplified by negative G. So it's negative G times Vi subtract beta times V out. Right? So to derive the transfer function, we know V out, which is at this point, is equal to negative G times Vi minus beta times V out. So simplify the equation, we multiply everything out. So it's negative G times Vi, negative G times negative beta times V out. So that becomes positive. And then we move the V out to the other side of the equation to collect the V out together. And simplify the equation a little bit. So it's V out multiply 1 minus G times beta. Whoa. I am missing something here. There you go. So it's V out times 1 minus G beta equals to minus G times Vi. And the transfer function is equal to V out divided by Vi. So we divide Vi to both sides of the equation. So we get V out over Vi is equal to negative G divided by 1 subtract G times beta. So this is now the transfer function. So there are two conditions, two criteria to cause this feedback loop to oscillate. So the first, the condition is that this term, the closed loop gain, which is G times beta, has to be 1. Okay, or you can say the the denominator has to be 0. Okay, so anything divided by 0 will give you infinity. So basically you feed it nothing and it just, the output just amplifies to infinity. So that's what an oscillation, that's what happens when there's an oscillation, is the denominator is equal to 0. So the two criteria for oscillation is 1, the closed loop gain, which is G times beta, has to be 1. So the closed loop gain has to be unity. And also the second criteria is the phase of the closed loop gain, okay, that's this term, has to be 0 degrees. So if the magnitude is 1 and the phase is 1, so what happens is 1 subtract 1 basically is 0. So that's what happens. That's what you need to make this thing oscillate. So that's the fundamental two criteria. If you understand that and you understand how to derive the transfer function, the circuit design will be super simple, and you will remember this for the rest of your life, I promise. Let's go through a example of this feedback loop amplifier. This is the amplifier I designed last night. So here you have a classical output collector amplifier. It's an inverting amplifier. It's just a transistor, a NPN transistor here with some bias resistors and a choke here to prevent any RF from going through the supply rail, and two blocking caps, one at the input and one at the output. So these are pretty large value caps. I'm trying to design an oscillator at around 16 megahertz. So this is a 16 megahertz oscillator. Okay. So at 16 megahertz, this is such a huge cap that it becomes a short circuit. So it's like a short. So both the input cap and the output cap is just short. And this is a pretty big inductor, so it's like an open circuit for high frequency. So nothing will go through the collector. All right. So this is the classical inverting amp. So the input is here and the output is there. And the phase between the input and the output is 180 degrees. So it's an inverting amp. And then we have a classical feedback network here. And basically the output of the amp will be connected to the feedback network, and the output of the feedback network will connect back to the input. So this is your classical feedback amplifier design. So in order for I'll explain a little bit more how this thing works. So let's get started here at the beginning. At the input, the phase is 0 degrees coming in, and then you go through the amplifier. There's some gain, but it's an inverting gain, so the phase is 180 degrees at the output of this amplifier. Since this is such a huge cap, the phase is 0. It's just a short circuit. And then what happens is the first cap here, since you have a shunt cap, it adds 90 degrees to the phase of the incoming signal. So since it is 180 degrees here, by the time it gets to this cap, it adds 90 degrees to the signal. So now the signal is 270 degrees. Okay. And then you have this tank circuit made out of this inductor and this cap in series. At the resonant frequency, the L and C becomes a short circuit. Basically, the impedance of this inductor equals the impedance of this cap, so that when you add them up in series, it cancels out. It's like a short circuit, right? So it adds zero degrees of phase at this resonant frequency, and this is the resonant frequency where the circuit begins to oscillate, and I'll explain why. So again, at this point, this cap adds 90 degrees to the signal. So it went from 180 degrees to 270 degrees here. At resonant, the oscillation frequency, this is a short, so it's 0 degrees. So it adds 0 degrees of phase as the signal goes through here. And then you come to this another shunt cap here. Again, it will add 90 degrees to the signal. Since it is 270 degrees as it travels through here, it adds another 90. So now the phase becomes 360 degrees, which is also equal to 0 degrees. Okay, so now you have pretty much meet the second criteria, as we discussed before, that at the phase of the closed loop gain has to be 0 degrees. All right, So now we have satisfied that criteria just by going through the feedback loop. Right now, now the phase is 0 degrees going through the entire loop. So your closed loop is now 0 degrees. Now, how do we get to the first criteria where we have to have a unity gain, or a gain of 1? The closed loop gain has to be 1. Well, let's take a look at the circuit here. You realize, like, there's this feedback network that connects the output, which is here, to the input, right? Which is right here. This is also a short circuit because this cap is so huge. So this tank is a series LC. Remember, at resonant, this is a short circuit. So essentially what it's doing is it's shorting the output, which is here, to the input, which is here. So you're basically shorting the input to the output. So that's how you get unity gain. Basically, the input is equal to the output when you short it together. All right, so that is the second criteria where, to meet the oscillation criteria. So now we have both unity gain by shorting. You must have a tank circuit, an LC circuit here, or else this thing will not oscillate. There's a lot of mistakes on the internet where they don't populate this this capacitor, the CT. They just have this inductor, right? That will not work. I will tell you right now, you have to short the input to the output, or else you will not get a unity gain and this circuit will never oscillate. So there's a lot of mistakes out there on the internet, so don't fall for that. I've been doing this for many decades, and I've seen these mistakes all over the place. So you have to have a tank circuit. Okay, so by doing that, you meet both criteria. You need, you'll meet the unity gain, and you also meet the 0 degrees closed loop gain phase. All right, so that's how it works. So here's a little breadboard that I did last night with just a NPN. This is a 2N 3904 transistor. It's an NPN transistor, and you got your classical caps and inductors and whatnot. And then let me see if I can open this guy. So this is the result of the oscillator, and you can see it's a beautiful sine wave. The peak to peak was about 6 volt, and the oscillation frequency is about 16 megahertz. That's it. Just wanna to show you guys how an oscillator works, and thanks for watching. All right, bye.